So for 15, it's pretty easy. You can do it in your head. But suppose you took two 200-digit numbers. Well, with enough patience and paper and pencil, you could multiply them together to get a 400-digit number. And computers can do that in a snap. But if I gave you the 400-digit number and told you, find the two 200-digit numbers that were multiplied to get it, I don't think you can do it. And in fact, even the world's most powerful computers, that is a problem which is essentially impossible for them to solve. The factoring problem is used to encode most of the important secret messages that are sent today. The way it works is that, say, when you buy something over the internet, your computer multiplies two 200-digit numbers together to get the 400-digit number. And now, anyone can encode things if they know the 400-digit number, but to decode it, you need to know the two 200-digit numbers. And nobody can figure those out from the 400-digit number because the factoring problem is almost impossible to solve.
Shor's discovery was so exciting because what Shor says, essentially, is give me a quantum computer and I'll be able to crack the most common and most important way to encode secrets.
Governments take the development of a quantum computer very seriously. As a threat, a quantum computer can break many of the encryption codes that are in use today, including those codes used on satellites, those used by banks and credit cards for secure communications.
But just as theoretical physicists saw that a quantum computer could crack secret messages, they also realized that quantum effects could be used to create the world's ultimate secret codes, quantum codes, providing a super secret way to keep information private.
In classical cryptography, we usually make the assumption that the system is secure because the eavesdropper, the would-be eavesdropper, can't solve some difficult computational problem. Quantum cryptography works on a different principle. You can't break a quantum cryptographic code unless you can break the laws of physics.
With quantum cryptography, it's essentially impossible to eavesdrop on the transmission without being detected. We might call this the noisy observer effect. It's as if you were at a party and were listening in on a neighboring couple's conversation. They know instantly, without even looking, that they're being overheard.
Quantum cryptography is already being used at a high level, securing election results in Switzerland.
So in this lab, we developed the basic technology for quantum cryptography. What was secured by quantum cryptography is the fiber optic link that connects the place where the paper ballots are counted to the place where the state's computer are located. And that was the first public real-world applications of quantum information.
Quantum cryptography is just one of the many powerful quantum tools being developed and deployed at the moment. But the most fantastical and mind-bending application is a phenomenon known as quantum teleportation.
Quantum teleportation will not be anything like what you see in science fiction. The reason is that no matter is transmitted from point A to point B. It's the quantum information that gets transmitted from point A to point B.
Quantum teleportation is made possible by entanglement. One uses the entanglement of two photons to transmit the information from one over to the other one. In 2004, we did a quantum teleportation experiment across the river Danube. We ran a glass fiber cable from one bank to the other over a distance of 600 meters. This fiber ran through a sewer, and therefore we call it the third man experiment, remembering the movie The Third Man, which was staged in the sewers of Vienna, starring Orson Welles. This is the only movie where the theme is played by a zither. We create these entangled photons by shining a strong laser into a special crystal. And then a photon of higher energy can decay into two photons of lower energy, which are then entangled. We send one of the photons over to the other side of the river and keep the first one locally. This photon then meets a third one, the one to be teleported. By entangling these two, the quantum properties of the third one are transferred over to the particle on the other side of the river, and teleportation is finished.
So quantum teleportation is one of the most beautiful demonstrations of entanglement. So in quantum teleportation, we really have that something, quantum state or the ultimate structure of matter, disappears on one side and reappears on the other side without ever existing in between.
But the 2004 experiment is Schnee von gestern, which means yesterday's snow. In the long run, we want to go up to satellites, that way establishing quantum communication on a worldwide scale.
We now know the power of quantum information, but what will it take to realize the full potential of this technology? What will it take to build a quantum computer?
The principles of quantum computing are well understood. It is only their implementation in practice that is difficult.
There is no problem in principle with building quantum computer. That's very clear. We know how to put together strings of quantum operations on paper and how they will end up giving us a quantum computer. The problem is in translating it into real hardware.
We don't know what a quantum computer is going to look like because we don't have a quantum computer yet. We have a theoretical model of a quantum computer, and we're seeking and testing physical devices that could implement our theoretical model.
A quantum computer requires maintaining quantum superpositions to perform correctly.
Just like in the double-slit experiment, where the superposition and the resulting interference pattern on the screen were lost if the electron is observed or measured in any way. Similarly, the quantum computer derives its special power from maintaining large-scale superpositions of all of the qubits. This means keeping the quantum computer very well isolated from its surroundings and protected from any unwanted interactions until the computation is complete. Of course, this is a very difficult thing to do.
The major challenge in building a quantum computer is keeping it quantum. And that means keeping it completely isolated. Quantum systems have an annoying feature that when they spill out the information about themselves anywhere, they cease being quantum. So isolation is one of the key problems in building quantum computers.
Large quantum objects, or large physical objects, consist of billions of particles. Each of these particles is a quantum particle, but when large numbers of particles are put together, then each of these particles interacts with the environment.
For quantum systems, the environment refers to all of the things surrounding your system of quantum particles, things like dust or stray magnetic fields, background radiation, anything that can lead to an unwanted behavior in the system that you're trying to control.
Superposition states are very hard to preserve.
In Dr. Wineland's lab, the qubits are stored in what is called an ion trap.
Well, the analogy to our ion trap and a marble in the bowl is the following. We can think of the marble being the atom and the bowl being this so-called trap, the way we hold the atoms. And one thing we can do, for example, with our atoms and the marble in the bowl here is we can put the marble in a circular orbit going around the center of the bowl. And we can do this with our atoms as well. Now, with the marble in the bowl, we usually, at some instant of time, you realize that the atom, say, is going to be on the left side of the bowl or the right side of the bowl. Now, the strange thing in quantum systems, which allows us to make qubits, is that we can put the atom in a superposition state in its bowl, its trap, so that it's, at some instant of time, it's not on the left side of the bowl or the right side of the bowl. Rather, it's both on the left side of the bowl and the right side of the bowl at the same time. So the analogy with Schrodinger's cat is that we're able to make situations where we have a superposition of all the atoms pointing in one direction and all the atoms pointing in the opposite direction at the same time.
So what might a quantum computer look like?
Behind me, you see a prototype for a quantum computer. It's made of a very powerful magnet, which is made of superconducting material, which is bad at liquid helium at about -266 degrees Celsius. The qubits in that system are made of the small magnet inside of the nucleus of atoms. At the end of computation, we're using the magnetic field of these qubits to be able to read off the answer of the computation. This particular quantum computer has a dozen of quantum bits, or the equivalent of 1,000 classical bits, which is computers of the 1950s. If we're able to build a quantum computer with about 60 or 70 quantum bits, then we'll be able to have a quantum computer which is more powerful than all classical computers combined on Earth.
Today, scientists are pushing the limits of theory and experiment from blackboard to lab, harnessing the power of nature's mysterious quantum world, laying the foundation for a new era of discovery and innovation.
I think that the kinds of devices, the kinds of effects we're talking about may very well have a huge impact on future technology and on the way people live their lives. But you won't catch me telling you exactly what's going to happen. However, I think the most important thing about the future is that now that we're learning how to talk with atoms in their own language, in the language of quantum information, we can talk with them and deal with them in ways we never have before.
A wonderful possibility of transforming the way society works is to use superconducting transmission lines as a backbone for energy transmission. If you could use this quantum mechanical effect, which we can use, it's proven already, but if we could use it on large scale so that we could transmit power across the continent, then we could use renewable energy sources more efficiently, make the renewable energy sources where they're easy to engineer, and transmit the power to where we need it. I hope that this is going to happen soon. Certainly it could happen very soon.
Sure, quantum mechanics is weird. So was the idea of human flight before we discovered how to build planes and rockets to counteract the effects of gravity. Now we are taking off into the quantum future. By understanding how atoms and elementary particles behave at the most intimate level, at the level which they speak to each other in the language of quantum information, we can tame those savage quanta. We can cooperate with them to construct new ways of processing information, new ways of computing and communicating that will transform our life in a radical fashion. This way of thinking about the world, of understanding it at the level of quantum information, has the potential to transform every technology that we possess. And by transforming it and by learning to talk with these atoms and elementary particles, we'll find a new place for ourselves in the quantum world.